Welcome to week 5, video number 5, and welcome to my virtual office. This week we're going to talk about factoring polynomials. Step 1, we want to factor out the GCF if any exist. Step 2, count the number of terms. Step 3, if there are two terms, you want to check to see if it's the difference of two squares. If so, it would look like a squared minus b squared and factors into the quantity of a minus b times a plus b. Is it the sum of two squares? If that's the case, stop. This expression is prime and you should write it as prime. Next we have the difference of two cubes and the sum of two cubes. If so, it looks like a cubed minus b cubed or a cubed plus b cubed. If that's the case, it factors the exact same way except the signs are different. On a cubed minus b cubed, you'd have the quantity of a minus b times the quantity of a squared plus a times b plus b squared. And if it's a cubed plus b cubed, it would factor into the quantity of a plus b and the quantity of a squared minus ab plus b squared. Step 4, is it three terms? If it's three terms, it's a trinomial. Is it a perfect square trinomial? In that case, you'd have two different types. It would be a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. If both signs in the original trinomial are positive, then it factors into a plus b quantity squared, or if we have a negative and a positive, it factors into a minus b squared. The second type of trinomial is if the leading coefficient is equal to 1. For example, you would have x squared plus bx plus c. That factors into x plus m times the quantity of x plus n, where m and n equal c, m times n equals c, and m plus n equals b. These get a little more difficult. Now, if the leading coefficient is not equal to 1, you would factor by using grouping or with the AC method. I'm actually not going to cover that in this presentation. If you like that method, you may look it up in the book. Or B, use trial and error. The last is, are there four terms? If there are four terms, we're going to factor by grouping. And you should always check your work by multiplying out the factored form. And pay careful attention to the directions. I'm going to require you to check a lot of your work this week. So I'm going to show you a series of examples of each type. Factor the difference of two squares. Number 1, z squared minus 16, both squares separated by a negative. That factors into z plus 4, z minus 4. Another example would be 16m squared minus 81n squared, and that factors into 4m plus 9n, 4m minus 9n. Actually, take notice you are just using the factors of the square roots of the original binomial. In the last example here, number 3, I have 81a to the 4th minus 16b to the 4th. That will factor into 9a squared plus 4b squared times the quantity of 9a squared minus 4b squared. And the only thing different there is you can actually refactor the last set of parentheses. So now I have 3a plus 2b and 3a minus 2b. That is an example. Let me give you a real-life example. If I ask you to factor 12 and you just told me it was 4 and 3, you haven't factored it completely. So in this example, you have to factor the right-hand side another time. Again, notice if the binomial is the sum of two squares, stop. The expression is prime. Now, we have the sum of two cubes. That factors into a plus b because our original had a positive in it, and a squared minus ab plus b squared. Notice the pattern of the signs. If my original polynomial is positive, my factors are going to be plus, minus, plus. My first example is m cubed plus 27n cubed. It would be most helpful. I'm sorry, I have a distraction going on behind me. It would be m cubed plus 27n cubed, and that factors into m plus 3n times the quantity of m squared minus 3mn plus 9n squared. My next one is 5x cubed plus 40y cubed, and I'm looking at that and I notice that that 5 is not a perfect cube. Maybe it's a GCF, which that is exactly what it is. I'm going to factor that GCF out first. Then I'm able to factor the perfect cube binomial that has a positive in it. So my factors are 5 times the quantity of x plus 2y times the quantity of x squared minus 2xy plus 4y squared. Is it the difference of two cubes? Again, the same set of factors, only different signs. So I'm going to look at that first example. If my original perfect cube binomial is separated by a negative sign, my signs are going to be negative plus plus. So my factors for x cubed minus y to the sixth is x minus y squared. And the exponent of 6 is a perfect cube. Any multiple of 3 would be a perfect cube exponent. The second set of parentheses is x squared plus xy squared plus y to the fourth. My next example is 8m cubed minus 125n to the sixth. Again, perfect cubes separated by a negative, and you'll see the factors below there. Hopefully this is going to help you with the factoring. You'll get very good at factoring. Next, we're going to look at trinomials. And the first type of trinomials we'll look at are perfect square trinomials. My first example is z squared minus 10z plus 25. You have to have a couple conditions here. Is the first term a perfect square? Is the last term a perfect square? And is the middle 2 times the square root of the first and last term? Yes, it is. And so that will factor into the quantity of z minus 5 squared. We prefer it that way, but you can write it as z minus 5 times z minus 5. Especially if you want to check it, you could re-multiply by foiling. Letter B is the first term. Perfect square, 9x squared, yes it is 64y squared, a perfect square, and is 48xy 2 times or negative 2 times the square root of each end, and it is. So that factors into the quantity of 3x plus 8y, that quantity squared. Letter C. Now I'm looking at the 32, and that's not a perfect square, so maybe I have a GCF. And that is the case, so I'm going to factor that out, and it's 2. Now I have a perfect square binomial, 16m to the sixth minus 24m to the third plus 9. I can refactor that, bring my 2 along down into the factors, and I have 2 times the quantity of 4m cubed minus 3 quantity squared. In letter D, this one is so easy, I almost didn't bother to put it in there. I have x squared plus 6x plus 9. The square root of x squared is x. The square root of 9 is 3. That gives me 3x. And if I multiply it times 2, it's 6x. So that's a perfect square trinomial, and that factors into the quantity of x plus 3 squared. Next, I'm going to look at 3-term polynomials, factoring, where a is equal to 1. My first example is x squared plus 11x plus 18. Now I need to look at the factors of 18 that multiply together to give me 18 and add together to give me 11. Again, watch the signs in all of these because there's a pattern. I'm going to choose 9 times 2, and I factor that into x plus 9 times the quantity of x plus 2. My next one, I have to look at the factors of negative 14. Now you're going to see that my original trinomial has a positive and a negative sign. So my factors have to be both positive and negative. So do I want the factors negative 7 times 2, 7 times negative 2, 14 times negative 1, negative 14 times 1? You'll actually get very good at finding these factors. My factors for this trinomial, I'm going to choose 7 times negative 2, and that gives me x plus 7 times the quantity of x minus 2. C, now my signs are negative, positive. Therefore, I need both of my factors to be negative. Do I want the factors of 48 to be 48 times 1, 24 times 2, 16 times 3, and you can see all the factors there. I'm going to choose 16 times 3 because I know that adds to be negative 19, keeping in mind both signs have to be negative. My factors are x minus 16 times the quantity of x minus 3. My last example now would be where my original trinomial has both negatives. Now I need to have factors that have a positive and a negative in it. So this is where the trial and error comes in a lot. I'm going to set the factors up to be 3y plus minus 1y. And you don't really have to have the negative 1 there, but I put it there so that you could understand easily. My factors for this would be x plus 1y times the quantity of x minus 3y. Please remultiply these always to check. It's so easy to get the factor in the wrong position. Okay. Last type of trinomial is where my leading coefficient a is not equal to 1. Now I have to take into consideration the factors of the first term and the factors of the last term, and hopefully those factors multiply together to give me those terms and add together to give me the middle term. Sometimes you have to hit this by trial and error. The answer to this is 4x plus 3 times the quantity of x plus 4. Again, remultiply it to make sure that everything turns out okay. The last one is 40m squared minus 2m minus 24. And I noticed right away that there is a GCF there. That's always your first step. Look for the GCF. I'm going to factor that out. And again, the leading coefficient isn't 1, so I'm going to look at all of the factors of 20 and 12, and keeping in mind I have to get a negative 1 in the middle. My answer here is 2 times the quantity of 5n minus 4 times the quantity of 4m plus 3. My last slide on factoring is factoring by grouping. If I have a 4-piece polynomial, I'm going to break the 2 pieces into 2 sets of parentheses and see if there's a GCF in each side. On the left side, my GCF is x squared. When I factor that out, that gives me x squared times the quantity of x minus 4. I'm going to bring down the plus, and I see that 3 is a factor of the second set of parentheses. When I factor that out, I get x minus 4, and that is actually the red flag. If in your parentheses you do not get the same thing, then you probably have done something wrong, either a sign or you didn't get the whole GCF out. Okay, so my factors here then are x squared plus 3 times the quantity of x minus 4, because x minus 4 is actually my GCF in the set of factors in the step above. My next example, again, is a 4-piece polynomial. I'm going to break the 2 pieces apart, look for the GCF in each side. My first side, it's 5x squared. I factor that out, and that gives me 3x minus 2. But now when I look at the right-hand side, I don't really see a GCF. However, I'm going to bring down the negative, and I'm going to factor out a negative 1. And that will give me 3x minus 2. And I don't know what happened. My animation is a little off here. When I take the negative 1 out, I get 3x minus 2. In this expression, the 3x minus 2 is now my GCF. I'm going to factor that out, and my end result would be 5x squared minus 1 times 3x minus 2. Prove that to yourself that that would give you the 4-piece polynomial above by remultiplying. The last slide for tonight is solve equations by factoring. To solve equations by factoring, we want to use the zero product property and factor out the GCF. Letter A is already factored for you. Now I'm going to take both sets of factors, set them equal to 0, and I have 3x equals 0. I'm going to divide 3x by 3 and 0 by 3. I get x equals 0. My second set of factors, x plus 4 equals 0. I'm going to subtract 4 from both sides. I get x equals negative 4. My solution for this one is 0 and negative 4. Not only is that my solution, but it's also called my roots, my zeros, or it's my x-intercepts to the graph that that polynomial would create. The next one, I have two quantities set equal to 0. That's telling me I'm going to solve this. I'm going to set both equal to 0 and solve that by adding 1 on both sides and then dividing by 4. On the second part, I'm going to subtract 4 from both sides and divide by 3. I get my solutions to be negative 4/3 and 1/4. Again, these are my roots, my zeros, or my x-intercepts if I graph. The last one I want to show you on factoring is binomial that is not factored. So if I'm asking you to solve that, I need to factor it first into x times the quantity of x plus 8, set it equal to 0, and set each factor equal to 0. I would have x equals negative 8 and x equals 0. Thank you, and that's the end of the show for tonight. Watch out for the PS.